Hello everyone. We are here to present you a study we made to try to reproduce a famous drawing by Leonardo da Vinci. This study was conducted by a French and Italian group. So I am David Le Touzé, professor at École Centrale de Nantes. Here you have Andrea Colagrossi, researcher at Siena INM in Rome, and Salvatore Marrone, also researcher there in the same group. And the fourth author of this study is Andrea Colagrossi, who is a computer graphics specialist. He could not be present today, but he's part of this work. And now I will get a bit more inside the topic. So this work was done by us during the last 3 years. As you see here, we have a drawing by Leonardo da Vinci, which is very famous and which is linked to the word turbulence. So our group is working together for 15 years, and we are experts in fluid dynamics and especially in free surface flows. A free surface flow is a flow where you have both water and air and an interface in between. And we are experts in developing numerical methods to simulate this kind of flows. On the Leonardo da Vinci side, it is well known that Leonardo da Vinci was passionate by this kind of flows. He made many studies regarding hydraulics, where you have this kind of free surface flows, and there are hundreds of drawings of hydraulic situations. And this year, 2019, is the 500th anniversary of his death. Leonardo da Vinci was Italian, of course. He lived most part of his life in Italy, but in the last 3 years of his life, he went to France and he died in France in Amboise. A key key link between Leonardo da Vinci and fluid dynamics is the word turbulence. Because turbulence, which is one of the main phenomena in fluid dynamics, was named by Leonardo da Vinci. This word of turbulence was used for the first time by Leonardo da Vinci in this context, in the context of fluid dynamics. So there is an obvious link between fluid dynamics and Leonardo da Vinci. And also this drawing is often linked to this word turbulence, and it is famous. And you see here that you have an impact of water in a pool and complex free surface flows with complex phenomena. And this is the kind of flows we are specialists of. So this is why we decided to study this drawing specifically. So what we did during this study is try to answer the following questions. First, where does this particular drawing come from? What is its story? Why Leonardo did draw it, etc. And what was actually represented by Leonardo in this drawing? Because we don't know where it was, in which place in the world it was exactly, what was the size, what was the flow characteristic, like the flow rate which is entering this pool, etc. So then, after having done this historical part and investigation of the conditions, we wondered how we could reproduce it numerically with our tools, with which numerical method, how, etc. So we made some developments. And we wonder whether it was possible to visualize up to the details drawn by Leonardo, and maybe even more with our tools. And in the end, we will answer the last questions. Did we succeed? Did we reach something which resembles this drawing or not? And what are the differences and maybe why? And we will explain this. So we will start by the historical part. So when I said Leonardo was passionate with hydraulics, here you have one of his drawings. So these are the typical drawings he was doing. You see on the right part of this drawing. So this is the flow past pile, probably a bridge pile, the flow past the pile. And you see that he methodically draws every detail of the flow as he can see them, or even as he can imagine them. And here it is a self-portrait of him, and you see this attitude of observing and then drawing, which is his main thing. So observation and drawing for Leonardo da Vinci, it's really a method of investigation, and he used this both in science and in arts. So when he drew, drawing was his method to understand or to represent. Okay, so it was very important, and this is also why he's famous, because he made fantastic drawings of different natural or physical or artistic elements. So the link with the word turbulence, this particular drawing is often used by fluid dynamicists to represent this turbulence phenomenon, which we know quite well today, but it is very complex. We will discuss of it later on. And so you see here different fluid mechanics books on turbulence, which are illustrated by this specific drawing. So because this drawing is supposed to be one of the first illustration of what turbulence can be in a flow, even if it's a bit more complex than that. So what was the methodology of investigation we pursued? So the first thing we did was to study the story of this specific drawing among the body of other drawings of Leonardo. Where did he come from? What was also the scientific environment of Leonardo in terms of mathematical tools, of science advances at the time, and all the analysis in terms of history of science of these drawings, which were made in the 20th or 21st century. So we studied this literature. This was our starting point. The second thing we did is try through this study to investigate what are the actual conditions, what is the setting of this drawing, what is the size of this sluice, what is the flow rate which enters the pool, etc. Because if we want to reproduce it at some point, we need to understand what is the actual setting. And the third thing we did is that we analyzed, you see here below the drawing, there are some sentences by Leonardo, and in these sentences he explains what he drew, what he saw, and then what he drew. So we analyze this in terms of physics, and then we analyze the same thing with our knowledge of the physics, that is with modern physics, which is in terms of water, air, complex evolution, what can we see there in terms of turbulence, etc. Then, once we were rather convinced we would be able to do something with a numerical simulation, we chose a numerical simulation, and we studied different configuration, different setup, we made different assumptions, etc. At some points, there was the need of using a very big simulation, so we were compelled to use a supercomputer. And also, we were compelled to use a really advanced technique in terms of visualization to be able to interpret our large simulation. And the last thing we did in the end is with our best simulation, we compared what we had in this simulation to what was drawn by Leonardo and commented by Leonardo in his drawing. So the story is also a spatial story. You see here the path or the way Leonardo did between Vinci and Amboise when he came to France 3 years before his death. You see also here the Loire river, which is leisure in Latin, because there is a funny link with leisure. I will explain later on. And this historical way, we have extended it a bit to the south, up to Roma, and to the west, up to Nantes. But you see, we are geographically also within this the same space as Leonardo was at the time. So now that I have put this into place, Andrea will explain all the findings we made regarding the historical part, and I will leave him the floor.
Okay. As David told, our research on this Leonardo drawing started on September 2016 in Amboise. We were there during a weekend where we went up to the Loire from Nantes to Amboise. We visited the manor of Colagrossi, and which was residence of Leonardo da Vinci for the last 3 years before his death. And the beginning of the 16th century, we know that King Francis I of France invited Leonardo da Vinci to settle in the city of Amboise. And after the Leonardo death, his writing began to travel throughout to Europe, following a rather complex path. So now we want to see, I want just to show you and discuss a little bit this complex path. His notebooks are scattered today in different museums, in libraries across Europe, and they contain an amazing quantity of heterogeneous material, design for invention, scientific research, plans for unfinished works, caricatures, landscape, maps, emblems, architectural design, and iconic images such as the famous Vitruvian Man. In the next slide, I will briefly tell you how this the drawing we study leave the city of Amboise and reach its final destination. So, by Leonardo express will, after his death, the entire library is inherited to his student Francesco Melzi. 70 years later, the Leonardo death, the sculptor Pompeo Leoni bought part of these notebooks and manuscript, and Orazio Melzi, which is the son of Francesco, sell this book to all this material to Pompeo Leoni. Leoni dismembered this original manuscript and created 2 separate collections. The first one mainly is the Codex Atlanticus, preserved in Milan to the Ambrosian Library, and the second one is a combination of different drawing, mainly botany and anatomy, and was dismembered, and all the pamphlets are found in different European collections. After that, we lose the trace of our drawing, and which start his complicated path. So in 1589, Leoni moved in Spain, and he started also to separate the different Leonardo books, and the collection. Part of this collection that now was in Spain becomes the Madrid codes. Another part was sold to Lord Arundel, and goes to to England and becomes the Windsor Castle collection. And a picture of this library, and then another part come back in Italy and was bought by Galeazzo Arconati, and it becomes the Atlantic Codes, and now is in Milan to important library that is the Ambrosiano. Summarizing, before the Napoleonic era, we had 3 different main collections, one in Windsor, one in Madrid, and one in Milan. But then we have the story that Napoleone came in Italy and moved this collection in the Atlantic Codes in Paris. And then we have a funny story during the Austrian occupation, because there was a commission to resume the object taken from Milan, and part of this collection was taken and come back in Italy, Other part remain in Paris, just because since you see that Leonardo wrote in a reverse mode, this Austrian baron that take care of this, he start to think that this was like a Chinese book, and so he discard and remain there. So, why is so important the Atlantic codes for us? It is important because inside we have the first mention about turbulence, and in the sense of in the context of the fluid dynamics. And so you see that here it is this part in the Atlantic code in this sheet, and you see this sentence, and in this sentence it is very important because Leonardo starts to think about turbulence, where it is generated, where it is maintained, and where it is decayed. We start also to study some works about Professor Macagno, who was a professor at the University of Iowa, and he was an expert of all the Da Vinci study about hydrodynamics. And so in this different material, what we found is that he helped us to understand the word turbulence as defined by Da Vinci, which is different from a modern way of thinking. So essentially, Macagno wrote that the concept of turbulence for Leonardo is mainly linked to also to the transport of sediment. So where there is turbulence, then there is sediment transportation, and this means that if the turbulence is very energetic, we have that the turbidity of the water start to increase, and this is mainly the link that he has in mind. Now, in the modern way to the modern meaning that we have for the turbulence is different because it's not strictly related to the presence of the sediment. We know that turbulence is a regime of the flow in particular condition, and it depends by the ratio between the inertial force and the viscous force. But to have this concept, we have to wait the 1883, thanks to the experiment of Professor Reynolds in Manchester. So you can find different sentences on during the different document of Leonardo that confirm what Macagno said. Essentially, always when he talked about turbulence, he talked also about sediment transport. So now we can focus our attention on the Windsor collection, and as you see inside the Windsor collection, we have a very beautiful drawing of fluid dynamic problem. And finally, we can arrive to this the sheet number 912660, which is the drawing of our study. As you see, it is composed by two parts. In the first part, the upper part, we have the flow around a planar object that is inclined to the flow, and you can appreciate how we have all this detail about the free surface motion around this object. But in reality, what we focus our attention is the below part where we have this drawing. So this is the subject of our study, which is a flow of a stream of water from a sluice into a pool. So what we have is that the first things that we can see is that Leonardo correctly focus his attention on the fact that this kind of flow is a complex interaction between air and water. It is interesting that thanks to an infrared investigation of this drawing, we can see that Leonardo started its drawing focusing on the vorticity, on the vortex. So we have all the vortex here, and then after this he had other elements to this drawing. So now we can focus our attention on the sentence below the drawing, where Leonardo described in a very accurate way this fluid dynamic problem. In particular, he identified 5 different type of motion. In the first, we have the fact that the air is entrapped by the water. The second is that this air comes down in the pool in the form of a bubble. The third motion is the fact that this bubble wants to rise up. The fourth motion is what he calls this heavy movement of the water around the pool. And finally, he also identified a 5 motion. And the 5 motion is linked to the fact that some parts of the water rise up with the bubble, but there is also a part of the water that goes down to the pool and hits against the bottom. And also in this small sector, he also identified that there is part of the flow where the turbulence starts to decay, so the flow starts to slow down. So we can appreciate this kind of analysis that Leonardo did with this drawing, also taking other drawing. For example, here there is some parts taken by the 912662 sheet, and you see that he focuses his attention on this kind of different flow motion, and you can appreciate in this drawing that he focalized his attention one by one. So, for example, here his attention is on the air bubble. Here is in the vorticity, in the vortex. Here he focused the fact that the water jet goes down and hits the bottom of the pool. And so now I leave again the talk to David, that start to explain how we can manage all this kind of motion in a numerical simulation.
Okay, so as explained by Andrea, our questions in terms of fluid mechanics mainly relate around the link between turbulence and air-water interaction. Is it air-water interaction that triggers turbulence, or does turbulence influence air-water interaction? What is the contribution of both, etc.? This will be our main topic of research, and the main aspects we have to work on in our numerical model to be able to reproduce this complex flow. So to reproduce complex turbulent and flow with complex air-water interfaces like small bubbles, etc. The difficulty is that in terms of scales, these bubbles or these small vortices inside the flow, they go up to very, very small scales below the millimeter. And so it's difficult to have everything at the same time. This is the first thing, which is general, both for numerics and experiments. And regarding experiments, if we want to look inside the flow, which is transparent, what we can do is to lighten this flow with a laser and then track elements between one image or another. But if you do this with bubbles, you have lots of lights in terms of optics. It's very difficult to visualize. It's much easier when there are no bubble inside. Another technique is that we use to tell you the complexity is here there's a luminescence from biologic elements inside the flow, and we take their light and we are able to visualize energetic structures of the turbulent flow. But these are examples of a complex study to get information on the flow. And when you have this air and turbulence mixed together, this is very difficult, even with this kind of tools, to get something. So our only tool, more or less, or our main tool, will be the numerical simulation. So the method we will use is a specific numerical method, which is called smooth particle hydrodynamics, which is a method we are working on for 20 years now, both in Rome and in Nantes. It is specific because it is a meshless Lagrangian method. Meshless, it means that, as you see in this picture, we will represent the flow, like the water, as a set of blobs. You see those little blobs, and each blob in reality is a fluid element, but it's not connected to the others, contrary to other numerical methods. And each blob will be followed in its Lagrangian motion, that is, in its fluid dynamic motion, obeying the fluid dynamics laws. The last aspect of this method is that it is Hamiltonian, which means that it has very good properties in terms of conservation of mass, momentum, energy, in terms of mechanical conservation, which will be guaranteed by the method. And this is one asset of this method. So this method was born in the 70s for astrophysical flows, so for something very different. And later on in the 90s, it was extended to free surface flows, which are the flows of interest here. In terms of astrophysics, it's still used today. It's used, for instance, to study the formation of stars, this kind of complex astrophysical flows. And here you have an example of a giant simulation with 10 billion of particles. But coming back to free surface flows, with this method, there was a first attempt 5 years ago to study Leonardo's drawing. But this study was very preliminary due to two things. The first thing is that it was only made in 2D, and you see that the flow the author succeeded to obtain is quite far from what we can see from the drawing. And also, no air was modeled. So without the presence of air and only in 2D, it's okay. You can have a general idea, but you will remain very, very far from the drawing. So we decided to study this in 3D and with all the details of the flow in terms of air, water, and turbulence. And to do this, we will use the software we have developed in collaboration between Rome and Nantes. Which is now sold by a spin-off of Central Nantes, which is called SPH Flow. This software can do many complex free surface flows. You see here examples, and you see in each situation the complexity comes from the fact that the free surface is very complex in every situation. So this is really a method dedicated to simulate this kind of flows. And another tool we needed is, since we went up to do very large simulations in the end, we needed a supercomputer, and we used the supercomputer of Central Nantes. And in a funny way, this supercomputer is called Liger. So I'm back to my initial map. On this supercomputer, where we have a few hundreds of cores, in the end we made simulations. We required hundreds of thousands of calculation hours. With few million of calculation points, and in the end we end up with several hard disks of data. So there was also a complexity that we needed to send this data to the rendering colleague, and this was a little complex as well. So now I will leave the floor to Salvatore, who will explain all the details of the numerical method and what we did with it.
Okay, thank you, David. So we start from the Navi-Stokes equation, which came much later than Leonardo da Vinci. The first version of the Navi-Stokes equation came in 1830. And this is the version written in Lagrangian formalism for a weakly compressible medium. So you have the mass conservation equation, the momentum conservation, and then the advection of the fluid particle. This is the basic model that we use for our numerical solver. Then we need to add the turbulence. So to do that, generally, what we do is to model the subgrid scales. So we don't resolve all the scales, but we just add models for the very small scales. And to do that, generally, there are several models, and one of the most famous is the large eddy simulation. So we added the LES, the large eddy simulation model, to the SPH scheme. And to do that, we have some additional terms that are here that are used for modeling these subgrid scales that allow us to go to very high Reynolds numbers. And when we want to translate those equations in the discretized numerical model, so we have the discrete system, we have those differential terms, differential operators that are moved in summation over the particles. And here in blue you have those turbulent term that appears. And this was shown in a recent paper. So we started the work on the simulation. We started from very simple cases, because the very first question was which is the geometry of our problem. Because in the drawing of Leonardo, what we can see is only the jet, so the shape of the jet, and some very small features of the bubbles and of the vortex. But we don't know anything about the problem. We don't know if it's in a tank. We don't know if it's in a large basin. We don't know how the water comes. So we started with this question about the jet dimension, the tank size, the wall and the outlet configuration also, and the inlet conditions. So we started with the very small, simple 2D test cases, trying very different conditions for the inlet, for example, for the tank size, for the model to be used. And then we tackled also the identification of numerical parameters and CPU requirement, especially regarding the cost of the simulation. Here are some attempts of the 3D simulation, and as you can imagine, the particle resolution can induce a high CPU cost. So we have to take care also on which is the maximum size of our simulation for the results we want to obtain. And also here you can see different condition of outflow condition, because we need to take out the water for a long simulation. And then we had many other questions. One was about the air entrainment. If we need to put inside the air inside the jet or not, to obtain something similar to Leonardo's drawing, how do we track and how do we visualize the air-water interface, and also the vortex structures that Leonardo observes? So we have also a problem of visualization and post-processing. So we tried along this path to answer to this question. So these are examples of the very first simulation. This is the kind of visualization that we have. We can have a rough estimation of the free surface and some slices of the simulation. Here we have some vorticity. And what we can see are quantities such as, for example, the velocity modulus. So we can see the main features of the flow, but we cannot see many details. Here we understand, for example, in this simulation, that most of the energy goes down towards the bottom, and in the rest of the tank, the flow is almost at rest. But we need more details. So what we did, we asked to our colleague that is a graphical professional to help us. So we split the problem in two parts. One was the rendering of the free surface to have better visualization of the free surface and see the perturbation, or even locally, of the free surface. And the other part was the visualization of the vortex structure underneath the free surface. And in this case, we tried the different techniques to detect the vortex tube that are generated during the water entrainment. So these are two examples of what you obtained. Using different criterion for the vortex detection. This is using the modulus of the vorticity, and this is using the Q criterion that is related to the second invariant of the tensor of deformation gradient tensor. Here you can see that the jet, while it entrains, it go inside the water, it produces a lot of vortex structures, and these vortex structures goes on the bottom and then along the walls. And here you can see that the free surface is mostly unaffected by this jet entrainment. I will show you the full simulation of this first single phase simulation. So we have only the liquid phase. So you can see here the first jet that comes down, impact against the bottom, and then this annular vortex structures that develops and then impact against the wall and rise up along the wall. And you can see how many structures you have during this evolution. And anyway, the free surface remain mostly unperturbed during this evolution. So this is something that is still not in agreement with Leonardo's drawing. In this rendering, we go inside the flow also to take a look around and see more more closer the flow evolution. And this kind of details, Leonardo couldn't have anything about that. It's something that we have available now with our technology. We can see here we have a cut of the flow, and we can see a lot of details of the small structures that are produced. Anyway, even if the simulation was let's say very impressive for us, the final result, the final comparison with Leonardo's drawing was not so good. So we have that the free surface is completely flat, and all the vortex structures are on the bottom. There is nothing in front of the jet. So the idea was to add the air, that also Leonardo told us it was very important. So we used a more advanced model that was published in 2009, where also the air is taken into account. So we have air-water interaction, and we have surface tension. So we can simulate multiple bubble evolving in water. And this is what we obtain. And in this multi-phase simulation, here we have only the air phase. So we are looking only at the bubbles inside the water. So you can see that the bubbles come into the jet, and then they are merged in many other bubbles, and some of those are merged later on going to the free surface, bursting at the end on the free surface in a very complex manner. And if we compare just the modulus of the velocity of the two simulations, we see a rather important difference. That is, in the single phase simulation with the only liquid, we have that the flow goes directly on the bottom. While in the two-phase simulation, we have a deviation of the jet due to the buoyancy of the air, and then we have some detachment of the kinetic energy that goes up. And this is due to the bubbles that capture some of the water and make vortex structures going upwards. So this is the first clue that we are closer to the Leonardo's drawing. If we look to the vortex structures detected through the Q criterion, we can see that around the bubbles we have these kind of jellyfish shapes. We have these vortex structures with some tubes underneath that goes towards the free surface, and this is actually the vortex around the bubble, and then they burst at the free surface, giving rise to something close to what Leonardo was looking at. If we get closer to it, here there is a point of view from just underneath the free surface. We see that the bubbles chase up one after the other, and they evolve in a like toroidal shape when they burst at the free surface. So if we look at the final drawing, at the final picture, we have that we are able to capture the vortex detachment from the jet that is given by these vortex structures that are elongating from the central jet. Then we are able to capture these vortex torus that are given by the bubbles, the air bubbles, and these are shown here in this bursting of bubbles. And then we are still wondering about these trajectories of vortices, which can be also given by the wave, the perturbation on the free surface that is expanding around the jet. This is still an open question for us. So I will show you this just this final simulation of the two-phase flows, including the air. And this is the full render of this final simulation. So you can see here the bubbles rising up. These are the vortex tube that are colored through the velocity magnitude. And here we go through the flow, and we can see all the different bubbles rising and merging, and these like jellyfish shapes. And if we go inside the flow, here you can see this annular vortex. And here you can see closer this jellyfish shape. Also here on the free surface we can recognize some of the features drawn by Leonardo. And in this cut we have a cut. This is a cut of the simulation of the tank. We can see clearer this effect. So concluding. We tried 500 years after the Leonardo's death in our French-Italian team. We tried to reproduce one of his most famous in the field of fluid dynamics drawing of Leonardo. Leonardo was a very fine observer, and he was able to distinguish and to separate different flow features as a real analysis of the flow, like scientists does now every day. His tool was the drawing. He was not. He didn't have at that time the mathematical tools for writing laws. But with his drawing, he was able to really analyze those flow and the different features of the flow. And one of the most important feature was this air entrainment that he drew many times in his hydraulic flows. This kind of flows is very challenging for us, even today, even nowadays with our tools. So to do that, we use the quite advanced numerical method that is the smoothed particle hydrodynamics. It's a kind of frontier numerical method, something that is still not a standard method. And to reproduce his drawing, we tried producing the different successive hypotheses on the flow conditions. At the end, we achieved reaching a quite good condition, and we performed some 3D numerical simulation on a supercomputer with a large number of particles, something like 50 millions of particles. So we needed also a complex 3D rendering for this, and for visualize the different details. With the help of this graphical rendering, we were able to spot some typical features of the Leonardo's drawing. And for example, we saw that the air entrainment is responsible for most of the vortex structure seen by Leonardo at the free surface, at the liquid free surface, and so this air entrainment is crucial in the simulation. And then at the end, we saw that the final result of our simulation and the Leonardo's drawing is actually very similar in terms of essential features. And even if, of course, we need some more work on the analysis of the data and in the processing of it. So I want to thank all these people that gave a contribution, a fundamental contribution to this work. So it's a work of a lot of people, and I would like to thank you all them, and that's all. Thank you for your attention.